The search for sunlight is long and winding, quite literally, in fact, for the cucumber plant. As climbing plants, they make use of tendrils, specialized thread-like extensions that swing around in search of a structure to latch onto. Once tethered in place, a tendril pulls the rest of the plant up behind it. Historically, the study of plant tendrils has been documented since the 18th century. Notably, Darwin described tendril coils as a series of soft springs. Since then, we have come a long way in describing their anatomy and mechanics. It is known, for instance, that the suspended portion of a tendril coils into a helical shape with at least two oppositely handed helices connected by a helical perversion. This helical coiling shortens the tendril lengthwise, hoisting the plant toward the attachment point. Our recent findings have determined even more mechanical and mathematical specifics of tendril coiling. This coiling is made possible by a stiff ribbon-like strip of specialized cells within tendrils called the fiber ribbon. During coiling, the fiber ribbon contracts asymmetrically. When the tendril is ready to coil, a chemical compound called lignin accumulates in the ventral side of the ribbon. This stiffens the ventral side, shortening it relative to the dorsal side. An artificial model of this process is depicted here. It unwinds and flattens as it is pulled from both ends. To create the model, start with an unstrained silicone rubber strip and stretch it axially. Apply a silicone caulk layer and allow it to cure. It represents the most rudimentary of models, emulating nature to some extent, but not completely. Here is a natural tendril, acting in much the same way as the previous model. As it is extended, it unwinds to the point of flattening out. Now here is a natural tendril overwinding as it is extended. So, what causes this difference? Let's turn to a more complicated model. Here, we can observe a silicon model that has been adjusted to overwind instead of unwind upon stretching. This adjustment has been made by adding a copper wire to the exterior of its helix and a fabric ribbon to its interior. Together, the fabric ribbon and wire increase the model's effective bending stiffness with respect to twisting stiffness, making the intrinsic helix curvature harder to change while still allowing the model to twist around its center line. In other words, the model is less able to flatten out and more likely to add coils to compensate for the force being exerted on it from both ends. Mathematically, if the force needed to bend the material is less than the force required to twist it, there is more bending than twisting, and so the tendril unwinds on extension, flattening out. Young tendrils tend to unwind as they are typically easier to bend than to twist. In contrast, old tendrils tend to be harder to bend than to twist, and they overwind when pulled. But what does overwinding mean for the plant? Pulling leads to a two-phase response by the tendril. First, it acts like a soft spring while overwinding, but then it enters a second, more resistant phase as it begins to unwind. This unusual type of spring with a two-phase mechanical response has never been seen before in nature or in engineering design. Our investigations of cucumber tendrils provide insight into how these plants reach a vital resource, sunlight, and furthermore suggest a new design for springs that may prove useful in engineering.